Today we're going to be talking about changes of state and a more unique change of state called sublimation, and then we'll be discussing phase diagrams, which are pretty cool, and I'm going to walk you through a basic phase diagram. So I posted the notes, and the second page of the notes that goes with this is the phase diagram that I'm going to be reviewing, so you can fill yours out as I'm going through it. If you don't have a printer, that's okay. Maybe write down the answers so that you can save your own digital copy. But that's going to be my way of teaching you guys phase diagrams. And then the assignment for today is to try analyzing another phase diagram in a separate sheet. So you don't have to pass in the notes and the one I'm going over with. It'll be clear which one is the actual assignment and which one is the lesson. So, moving on. The little questions that they all have is, where does rainwater go when the puddle dries up? Well, we know that there's a water cycle, so the water is going to evaporate and basically go up into the sky and then come back down later as rain. But first we're going to be talking about sublimation. And sublimation is pretty cool, but it only happens to certain substances under certain conditions. Basically, sublimation is where a substance goes from a solid directly to a gas without passing through the liquid stage. So basically it goes solid to gas, completely skipping the liquid stage. And most substances can't do this, only some can. So this can occur because solids, like liquids, have a vapor pressure. So some substances, basically when they're ready to change state, when that vapor pressure is overcome, instead of going to liquid, they're going to go to the gas state. So this basically happens when vapor pressure exceeds atmospheric pressure at or near room temperature. So I like this. Basically, a solid changing to a vapor or a gas is sublimation. The opposite of that, vapor to solid, is called deposition. Just like melting and freezing are opposite, and evaporation and condensation are opposites. Sublimation as the opposite of deposition. So one substance that goes through sublimation is iodine. Basically, in this little setup here, the outer test tube contains solid iodine that's being heated. The inner test tube contains liquid water and ice. Basically, what's happening is that the solid is going directly to the gas, so there's no liquid stage in there. So it's pretty cool, and solid iodine will do this. So when the vapor reaches the cool surface on the inner test tube, it's going to go directly from the gas to the solid state again. So that's why it's a gas here, but as it cools back down near this test tube that has the ice, you see the solid iodine forming on the bottom of the test tube as it cools back down. So we kind of have a little contained system in here. The most useful substance that does sublimation is carbon dioxide. Solid carbon dioxide is known as dry ice, and that's really revolutionized the shipping industry because you can ship refrigerated goods, frozen goods, using dry ice, so that you don't have basically wet boxes as something is being shipped. So things that stay frozen during shipment, the dry ice is there to keep it really cold, and then as the dry ice does heat up, it's going to form just carbon dioxide gas. So that's kind of the one you've probably seen if you're ordering different materials that are refrigerated, they might come with dry ice. Dry ice is also fun to play with. So because it sublimes, it doesn't produce a liquid as ordinary ice, and as it changes state, the dry ice absorbs the heat, keeping the materials nearby nice and cool and dry. So that's why it's called dry ice. Water makes wet ice. So which of these describes a solid undergoing sublimation? Well, the answer is going to be A, where the vapor pressure exceeds the atmospheric pressure, then the substance would sublime or undergo sublimation. So second half of the lesson today is introducing phase diagrams. And I think these things are really cool because you can actually manipulate different substances, how they're changing state by changing temperature and pressure. So I'm going to walk you through what a phase diagram is here on the notes, and then we'll do a little lesson on how to analyze the phase diagrams. So the relationship between solid, liquid, and gas or vapor state of a substance in a sealed container can be represented in a single graph called a phase diagram. And a phase diagram basically gives all the conditions of temperature and pressure where a substance will be a solid, liquid, or a gas. And different substances need different phase diagrams in order to represent them. So pressure and temperature, basically the condition of pressure and temperature at which two phases exist in equilibrium are indicated by lines separating the phases. So there's lines basically showing you where a substance is going to melt or freeze or boil. So basically we're going to go across the lines for the different states. So here's a phase diagram. And I'm just going to get the different parts here to explain. So basically a phase diagram, they all have this similar kind of Y curvature pattern. You read them always solid, liquid, gas state. The line between solid and liquid is where a substance is going to melt. The line between liquid and vapor is the boiling point. But notice here that these are on curves. So if you change the pressure, that's going to manipulate the boiling point and the normal melting point. So but these are all single phases, and this is one for water, a phase diagram for water. Different substances are going to have different phase diagrams. So this curved line basically represents the barrier between the liquid and the vapor phase. So right on this line is the equilibrium. Basically, that's the boiling point. The other lines here, this is equilibrium between solid and liquid, so that's the melting point. And then down here, there's actually the equilibrium between solid and vapor. So yes, water can sublime, but it would have to be very, very low pressure and very low temperature. So just seeing what the different lines are. But if you can manipulate these conditions, you can manipulate the changes that a substance is going through. So this little circle on the diagram is known as the triple point. And this is where all phases, solid, liquid, and gas, would exist at the same time. And I'll have a video of you guys showing you the triple point of water. But that happens way down here at a low pressure of 0.61 kPa and a pretty cold temperature, basically just above freezing. 0 degrees Celsius would be the triple point. So the triple point describes the set of conditions where all three phases exist at the same time. And it's weird. Basically, at the triple point, you would have water that is boiling and freezing and existing as a liquid at the same time. In order to do it, you basically got to lower the pressure, so it would have to be done using a vacuum in a closed container, and I'll post a video for you showing you that. So just going into Earth again, this question from before, that liquid water evaporates, rises to the atmosphere, then it forms clouds, that's condensation, and then rain falls back down to Earth as a liquid. Looking back at a phase diagram for a couple more points. And I'll show you this with when I get to that second phase diagram part. So basically, if you manipulate the pressure, that's going to change the boiling point. So a decrease in pressure, so pressure is on the y-axis. So at regular conditions, when we talk about the normal boiling point, that means at standard atmospheric pressure. So that's the normal boiling point. Right here, there's 101.3 kPa, or you might see phase diagrams that have 1 atmosphere. That's standard. That's a standard atmosphere. And so we say the temperature where a substance melts or boils at the standard atmosphere is the normal melting point and the normal boiling point. So we're going along this standard line. So if I decrease the pressure, so the pressure is going to go down, that's going to change the melting point. So you'll see that as the pressure goes down, it's going to melt at higher temperatures, and it's going to boil at lower temperatures. An increase in pressure is going to raise, so if I go up, so if the increase in pressure is going to raise the boiling point, but also lower the melting point. So water is a little bit of an interesting one. But basically, if we change the pressure, so my pressure is going up, now the pressure going up, the water is going to boil at a higher temperature, and it's going to melt at a lower temperature. Increasing the pressure won't change the vapor to a liquid. So basically, if you increase that pressure there, the solid and vapor in equilibrium at temperatures below, the solid and vapor are in equilibrium at temperatures below this point here. So once we get down here, if the pressure is low enough, then we're just going to go between solid and vapor. Okay. All right, now I'm going to show you guys and go through, I'm going to go through with your notes, like this here. These are the notes. So you guys have your notes basically that looks at the phase diagram here. I'm going to give you a little walkthrough using this phase diagram as well, and I'm going to do my best to kind of following the cursor. So the first thing you want to do with any phase diagram is identify where the solid, liquid, and gas areas are. So it always goes solid, liquid, gas. So this part here, I'm going to do S for solid, L for liquid, and G for gas. So that way you can see where everybody is. And you'll note, and this line here is basically the line between solid and liquid, so that's the melting freezing line. Over here is your vaporization line between liquid and gas. In different substances, the phase diagrams will look a little bit different. So now let's look down below, and we're going to analyze our phase diagram. So first question here is, what is the normal freezing point of the substance? So the freezing point we want to look at is basically between the liquid and the solid. So normal means normal conditions, so that in this case, this is atmospheres as our y-axis. So we're going to look at one atmosphere, do a nice straight line over, and then look down to see what temperature we're at on the line. So that goes down to 100 degrees Celsius. So that would be the normal freezing temperature. We're going to do the same thing for the normal boiling point. We're going to go across our pressure all the way over. We're at 1 atmosphere for pressure. And I went over to that line between the liquid and the gas. And I'm going to kind of go down. It looks like I'm right below 400. So I'm going to call that, let's call that about 375 degrees Celsius. Oops, what happened there? So 375 degrees Celsius would be the normal boiling point. Next question is, what's the normal melting point? Well, melting and freezing occur at the same temperature, same thing as boiling and condensation. So at that 1 atmosphere, it's also going to be 100 degrees Celsius. I also get a couple other questions. So if I had a quantity of this substance at a pressure of 1.25 atmospheres, so there's our pressure, and a temperature of 300 degrees Celsius. So we're at 1.25 atmospheres, and I'm going to go over to 300 degrees Celsius. So I'm right about here, so our substance is a liquid. Now we're going to lower the pressure to 0.25 atmospheres. So in lowering the pressure, I'm going to go across this transition line from liquid to gas to get down to 0.25. So the question asks, what phase transition are going to occur? Well, we started up here in the liquid area. Now we're going to move down to gas. So liquid to gas is vaporization. So I would say that vaporization would occur at around the line here. If we were at 300, I'd say when we cross that line here, that's about 0.75 atmospheres if I bring that over. But it would definitely vaporize, so at about 0.75 atmospheres, ATM. So at what temperature for 5 do the gas and liquid phases become indistinguishable from each other? So basically another thing with phase diagrams is this area over here. So here's your liquid area, here's your gas area. When temperatures get above this point, basically the liquid and the gas are indistinguishable from each other. They're just kind of blending in when the temperature gets high enough. So what temperature does this happen here? I can just draw a line straight down. So from this point down, we're at 8, basically 825. I'll say that's 825 degrees Celsius for that. And then last question, if I had a quantity of the substance at a pressure of 0.75 atmospheres and a temperature of 100, so 0.75 atmospheres and 100, so we're going to go over, so that puts us right in this liquid range. We want to know what phase change is going to happen if I increase the temperature to 600. So we're here, we're going to go to 600. So we're going to cross this line, and then we want to know at what temperature would that change occur. So if we take a look here, so we're starting 0.75 and 100. So that actually 0.75 and 100, that actually puts us kind of right on this line here, taking a look at it. So if we are increasing the temperature, we're actually going across two lines. We're going to go across the solid liquid line, basically right at 100. We're going to go across the solid liquid line, and then if we keep going, very shortly after, we're going to cross the liquid to gas line, and I'd say that happens below 200. So let's call that 175. But basically, we started here, and we're going to go. We started at -100 Celsius. I misread. So at -100 Celsius, then we're going to cross at 100, and then looks like soon after at 175, we're going to cross again. So basically, we are going to, what phase changes are going to occur? We're going to melt, then vaporize. And when these things happen, we would say we melt at 100 Celsius and vaporize soon after at about 175 Celsius. So again, that was moving across this line. We started at -100, we moved over the transition line, and then we moved over the transition line again to go to 600 degrees Celsius. So these phase diagrams, there's a lot of manipulation that you can do with them, and the questions a lot of times will say, if I increase the pressure, if I change the temperature, what's going to be changing? So take a look at today's assignment, which is a phase diagram worksheet. You'll be able to type right in it, and let me know if you have any questions.